This is a very short lecture on radiation quality. We want to introduce the concept of radiation quality and describe how we measure quality. First of all, what do we mean by radiation quality? Radiation quality is a measurement of how penetrating the radiation is. Once we know radiation quality, we can estimate dose rate at points in a medium or the patient. We can estimate the differences in the energy absorption between regions of different composition, and we can also estimate the biological effectiveness of the radiation. We can specify quality completely by specifying the spectral distribution of the photons. Unfortunately, this is generally very difficult to measure. What we're going to try to do is specify the quality by maybe one or two numbers that will characterize the beam of radiation. And if we have a gamma ray beam, it's very simple to specify the quality because all we need to do is specify the energy of the gamma rays. You know, we know exactly what's coming out of a gamma ray source. A low energy X-ray beam, we have to specify two parameters. We have to specify the potential difference across the X-ray tube, and we have to specify the half value layer of the radiation. The reason is that in most X-ray tubes, both diagnostic and therapy, we'll put some kind of filtration in to selectively attenuate low energy X-rays. So because of the differences in filtration, the beams are going to have different characteristics, and we need the two numbers to specify the quality. For megavoltage beams, all we need to do is specify the maximum photon energy. So how do we measure half value layer in a practical point of view? Let's recall the definition. Half value layer is defined as the thickness of material that reduces exposure rate to half its initial value. Another quantity is the homogeneity coefficient, which is the first half value layer divided by the second half value layer. It's a measurement of how homogeneous the X-ray beam is. Remember, the filtration that we put to measure half value layer will also modify the quality of a heterogeneous beam. So second half value layer will typically be greater than first half value layer. Third half value layer typically greater than second. So to measure half value layer, we place an absorber in the beam, put in various thicknesses of absorber, and measure the attenuation. Well, first the issue is what absorber do you use? The absorber depends on the energy of the beam. If you're in the kilovoltage range, aluminum is a good absorber because you'll be putting in millimeters of aluminum. Up to about 3 MV, copper would be a good absorber. Going to higher energies, lead would be your absorber. So that's the first issue. The second issue is the requirement of narrow beam or good geometry. And the reason for good geometry is you don't want scattered radiation to reach your detector. So here's a difference between narrow beam geometry and broad beam geometry. Narrow beam geometry, you collimate the beam very tightly. You place the attenuator close to the collimators. You put the detector far away from the attenuator. Consequently, any radiation that's scattered in the attenuator is likely to be deflected away from the detector. Broad beam geometry, you have wide collimation and the detector is placed close to the attenuator. Consequently, scattered radiation from the attenuator can reach the detector. For measuring half value layers, you really want narrow beam geometry. The only exception to this rule is if you're measuring half value layers for shielding purposes. When we talk about radiation shielding, we want to look at a worst case scenario. Broad radiation beam, somebody is next to the wall of the therapy room, so that's broad beam. We want to use broad beam values. For most of the time, we want narrow beam values. So once we have the half value layer, we can determine an effective energy of the beam. the definition of an effective energy is the energy of the photons in a monoenergetic beam that will be attenuated at the same rate as the actual X-ray beam. And typically, the effective energy of an X-ray beam is approximately 1/3 the maximum energy. So, what are the factors that affect beam quality? First, the most important factor is the electron energy. The energy of the electrons that are used to produce the Bremsstrahlung X-rays, the accelerating potential. For example, in a 10 MV X-ray beam, you'll accelerate the electrons to 10 million electron volts. That's the main factor. The other factor is added filtration, and that occurs mainly with orthovoltage X-rays. You put in added filtration to selectively absorb the lower energy photons. Now, one of the things that occurs with orthovoltage filters is we may want to use higher Z materials to more effectively absorb low energy photons. So we may want to use, for example, copper as a filter. The problem with using copper as a filter for an X-ray beam is the production of characteristic X-rays in copper. So you've filtered out low energy photons from the X-ray beam, but you're left with some low energy characteristic X-rays from copper. So a guy named Thoreus had a great idea. He said, well, let's sandwich filter. Let's put a sandwich kind of filter. So once we have the copper filter, let's put an aluminum filter beyond the copper filter to filter out the low energy characteristic X-rays from copper. And the even lower characteristic X-rays from aluminum are not an issue. So if we use a copper filter, we'll use an aluminum filter along with it. If we use tin as our filtration material, which is used to filter out a higher energy orthovoltage beam, we'll then use copper and aluminum to help filter out. We'll use copper to filter out the tin characteristic X-rays and aluminum to filter out the copper characteristic X-rays. And these are called Thoreus filters. Low Z filter material, which absorbs the characteristic X-rays produced by the X-rays absorbed in the higher Z filter. Okay.